different workshops. Sorry, someone has to say something.
Rogerio, did you mention? I think it was mentioned about the picture.
Yeah, I'm going to mention the picture.
Ah, okay, very well.
Yes, yes. So I have a couple of announcements before starting, and the first one is about the picture. Thank you, Mustafa. So we're going to take the picture after the introduction, the usual introduction, before the questions today. Okay. So I ask you all to open your cameras, and Tiago, actually, I have to. Tiago is the guy who's behind all of this. He's doing all this background work. Tiago Cudinotto. And of course, I want to thank him for all this and take pictures and before the question. And the other announcement is that this is a different workshop. It's the first time we're trying this format. So we're going to pass around. You're going to receive a very brief questionnaire. So it's important for us to get some feedback to see your impressions, and I'm sure there are several ways we can improve this format. So please fill this out. Okay, so we're the usual format. So the presenters of the talks will give 2-3 minutes reviews of the main points of their talks, because everybody saw their videos, which, by the way, were amazing. Thank you very much for the videos; they're fantastic. And then the poster presenters will also introduce themselves. We take the picture, and we start the questions. Okay. So Chris, you're first. So your talk was about calibrating detectors for precision cosmology. Please go ahead.
Thank you. So my talk was about calibrating detectors. And this is with a particular emphasis on the Roman Space Telescope. And I did this both because calibration is, of course, essential to all of our cosmological probes, and also because it's an area where, with the kind of work we do with dealing with large data sets and statistical analyses and correlation functions and so on, I think it's a great opportunity. So my presentation was focused, of course, on the Roman Space Telescope, which will be an upcoming mission, and on the weak lensing aspects of that, where I'm the topic lead. And of course, we have many types of systematic errors in weak lensing, and my focus was on things related to detectors, which are one piece of the overall signal chain in a cosmological measurement. So we have infrared detectors for this mission, which have their own interesting features. I could spend many hours talking about them, but the interesting feature of infrared detectors from our point of view is that these devices, unlike a CCD, you can read out many times. And it's by taking many samples of the image in your detector and looking at how the signal is building up with time, you can get a lot more information this way. So in this talk, we used flat field data where the detectors were just diffusely illuminated in the laboratory, actually before we select which ones we are going to fly. And if you look at the Poisson-induced fluctuations in the flat field images, just you repeat the same experiment many times and look at those fluctuations, there are correlations between the pixels in your images that provide an enormous amount of information on what is going on in your detectors, and in particular on things like crosstalk between pixels that could affect a precision measurement, like for my interest, weak lensing, but any of the cosmological probes and other astrophysical applications as well. So yeah, that was the main thrust of my presentation.
Thank you, Chris. So next is Benjamin. So Benjamin had a talk about lifting cosmic mysteries with new approaches to cosmological inferences. So, and just summarize a few points, Benjamin.
Hold on a sec. I need to find the right thing to share. Let me make sure they have that ready. Okay. There we go. All right, can you see my slides?
Yes.
Yes.
Oh, good.
Very good.
All right, so let me just give you the brief summary. So main point is we have a lot of data in cosmology, and that's a good thing. And in fact, over the next 5 years, there'll be another really step change, another big change in the amount of data that we'll have available, with a number of new instruments coming online. Data will be released from space and from the ground. And so what are we going to do with all this data? This data will cover the entire range of observable scales on the light cone. And so it'll give us an unprecedented view of the universe. So if you want to attack this problem of learning about cosmology from these data sets in the most general way, really the way to think about it is in terms of a forward model where we start with a set of initial conditions, symbolized here through this ball of initial curvature perturbations. These are parameterized by some set of physical parameters, and they're then modeled forward through the, well, I'll get to exactly what's going on, but there's a bunch of parameters as well that model the content and the dynamics of the universe. And here are all the things that we then observe, which are all of the physics here is in this forward model. And what we want to do is to flip that arrow around and go backwards and take all this, all these data sets that are probing the universe in various ways and get the best possible constraints we can on these parameters and even on the details of these initial conditions. So here's the summary of that. Essentially, these subject areas typically are discussed in separate ways. People are talking about the initial conditions, talking about studying growth of perturbations, studying dynamics of the perturbations, or constraining the expansion geometry. They're tied together by the three, what I consider really the three fundamental questions in cosmology, which are questions about cosmic beginning, questions about cosmic content, so what is in the universe, and questions about cosmic fate, having to do with the nature of the acceleration, which is a big mystery, obviously. So that includes whether that's dark energy or what that is. And so here I have a big busy slide, which basically give a bunch of key phrases from my talk. I basically set out two different ways to think about this inference problem. One in terms of a full detailed likelihood-based forward model that then allows you to put in the observations and then sample over all of the unknowns, including all the initial conditions, this 3D ball that I showed you. You get samples of that. And over histories of the universe. The difficulty there is that you have to get the model really precise, take advantage of the statistical power and data. And so the alternative way to go about this is to give yourself the freedom to model and the freedom to also cut and project the data in various ways. And that is what people call simulation-based inferences. So here there's also simulations in this likelihood-based forward model, but here there's only forward simulations. So you just run a lot of simulations forward, and then you have some machinery that takes that and turns it around into constraints about parameters. And so we have a package that does that called PyDelphi. And along the way, I talked about another way of dealing with this difficulty of modeling the details of exactly how these perturbations get transported to the observations that we see, and to look at geometrical tests. I discussed a class of cosmological tests that we've developed, which are related to the Aker-Kuczynski test, but there are generalizations of it in terms of actually looking at the full field and looking at multiple tracers, and not just in redshift space, but also in combination with other probes. I talked about machine learning innovations that make a lot of this possible. For example, neural physical engines to build bias models, neural density estimation, which we use here to infer the likelihoods from these forward simulations. Information maximizing neural networks, which are automatic ways of finding all of the relevant compression quantities from data sets based on simulations. Wasserstein-GANs, which are ways of generating, of training networks to generate simulations. And then I talked about, since this is simulation-based, I also talked about some simulation innovations. So the fact that we now have methods to run perfectly in parallel, n-body simulations perfectly in parallel, which allows using a lot of different computational platforms to do that. Ways to super resolve n-body simulations, again using machine learning. A new way of doing variance reduction on simulations, so you need a lot fewer detailed simulations, which means you can be much more precise in your simulations. And then I mentioned some projects where we produced a lot of simulations and put them online in collaboration with a large group of other people. And one thing I didn't show in my talk, in the video, which I wanted to correct, is this last slide, which are links to all of the codes. And if you go to the PDF version of the talk, that's the last slide. And so you can go and follow up and look at some of these codes.
Thank you, Benjamin. So next is Matthias. Matthias talked about assorted results in effective field theory of large-scale structure.
Great, sounds good. Let me share my screen. Let's see. Okay. So for several years now, I have been working on what is perhaps a very old school way of making predictions for upcoming experiments and existing experiments, which is just basically an analytical approach, just perturbation theory. So I just, in this few minutes, maybe I motivate this approach because it's so old school that it looks like it's not what people should be doing. But this plot shows in our modeling of the BOSS data, the 2-point function, the power spectrum of the BOSS data, you can see the linear theory prediction for the power spectrum, that's a solid line. In this perturbative approach, you expand in powers of the power spectrum. The first next to leading order correction is the so-called one loop correction, that's the blue line. The shot noise is the horizontal line. And so x-axis is scale, y-axis is the power spectrum, and the green dots is for some binning of the data, the error bars. And what this is supposed to convey is the fact that on the scales from where we get information in these surveys, and I think this continues to be true in upcoming surveys, which is say around k maximum of 0.2, somewhere in that range. The one loop correction, the lower, these are the lowest redshift for the BOSS survey, so 0.3 or something like that. this one loop correction is a 10% effect. So it's not such a big deal. And if you were to go one order next, and you were talking about 1% type effects and so on. So so you can get very accurate predictions with a few terms in this expansion. And I think that's the reason why perturbative approach is not a bad one. You just need to do a few terms. It's not such a big deal. But what the green points show is that the error bars are really, really very small. They are at the percent or sub-percent level, and they get smaller as we go to future surveys that were mentioned in the previous talks. So you really need to, the difficulty is not so much that the size of the corrections are large, but you need to really be very careful because the statistical power is very high. And so I think what is afforded to you by being able to do analytical calculations is that you have more control about how many terms to include. You can have some, I mean, the big difficulty is the relationship between your tracers and your underlying density field, which you have to model somehow. In this way, in this particular approach, at least you have a set of terms that a very well-defined set of rules to include how many bias parameters and how many scale-dependent terms you need to put and so on. So maybe too conservative, maybe you have too many many terms, and maybe you are not including some of the physical constraints that you might know about them, but at least you're sure that it should span the reality as you vary those parameters. And so it's a good approach to be a little bit more perhaps conservative and be able to marginalize over these things. So that's the motivation. In the talk, I mentioned results from BOSS survey to measure the Hubble constant, that surprisingly you can get a decent constraint compared to Planck without using CMB data. With error bars that are comparable, perhaps surprisingly, and a few other things that we've been thinking about. But I think I'll just stop there. I think this is the main takeaway from me.
Thank you, Matias. So next is Ariel Sanchez with his Gabriel Garcia Marquez inspired title of Let's Bury the Prehistoric Age.
Yes, let me see. Combine that share screen. Okay. Yes. Can you see my slides?
Yes.
Yes. Okay. Yeah. So I will try to be very brief. My talk was focused on a very, very simple problem, but I think that it's an important one. And it's part of my personal crusade against megaparsecs over H units in observational cosmology. These units are everywhere, and we just accept that this is the way we should express our models and our data. But in this talk, I try to present some arguments against this practice. So just to the main message is that it is of course fine to express measurements in units of megaparsecs over H. There's nothing wrong with it. The problems arise when we also express our model predictions in terms of in the same units, right? Because when we plot our measurements of the power spectrum also in megaparsecs over H units, we are forgetting the fact that before these models can be compared against data, they need to be corrected by Yarko-Paczynski distortions. And then in this step of correcting by Yarko-Paczynski distortions, these factors of H appearing everywhere in our units of the power spectrum just cancel out. So the fact that we plot our measurements in our models in megaparsecs over H units hides sometimes or obscures the dependency of these power spectrum predictions on the value of H. And the worst problem of all is related to the normalization of the power spectrum. We usually normalize theory predictions of P of k, so models of P of k in terms of sigma 8, the variance of matter in spheres of 8 megaparsecs over h. So that means that for models with different values of h, we normalize the power spectrum by the amplitude at a different reference scale in megaparsecs. So this has two effects. So when h changes, the value of sigma 8 changes due to two effects. One is the change in the amplitude of the power spectrum itself. When we change h to a fixed physical matter density, what we are doing is that essentially we are changing the dark energy density. So changing the dark energy density, of course, changes the growth rate of structure as a function of redshift, and this changes the amplitude of the power spectrum, and this, of course, enters in the value of sigma 8. But sigma 8 also changes when you change h, simply because when we change h, we are changing the value of the reference scale that we use to measure sigma 8 in megaparsecs. And this second point is the origin of a few problems that we need to pay attention to. These problems are related to, well, when we measure sigma 8 from observations, if we use data sets that have different constraining power on h, essentially we're asking our data, what is the amplitude of the power, what is the amplitude of density fluctuations on a scale of 8 megaparsecs over h? But if the data doesn't know what is the value of h, then that means that there is a big uncertainty on that number, just because the data cannot tell what is really the value of 8 megaparsecs over h. And then comparing constraints on sigma 8 from data sets with different posterior distributions on h might be confusing. And the second important issue related with these units is the way in which results of redshift space distortions are usually expressed. We often express measurements of growth rate of structure from redshift space distortions in terms of f sigma 8. And I showed that this is a problem, right? So this is not the best way to express these units. One way of these measurements, and one way of correcting these issues is to simply move from normalizing our theory predictions in terms of a scale in megaparsecs over h to a scale in megaparsecs. And what I propose to use is just to forget about sigma 8 and start using sigma 12, where sigma 12 is the measurement of the mass in spheres of 12 megaparsecs. So it's not using a scale in megaparsecs. And why 12 in particular? Of course, we could use whatever, any scale in megaparsecs would be fine. But I suggest to use 12 megaparsecs because for a value of h, like the ones that are preferred by Planck, 8 over h megaparsecs is approximately 12 megaparsecs. So the value of sigma 12 for a Planck cosmology is approximately the same as sigma 8, but these values differ for different cosmologies. So you can see the arguments behind this in the talk. And yeah, so the main message is this, that it is problematic to normalize theory predictions in terms of sigma 8. This leads to issues when we compare values of sigma 8 inferred from data sets with different posterior distributions on h. And yes, it is also problematic to express measurements of redshift space distortions in terms of f sigma 8. And both of these issues could be avoided if we just look at analyze the amplitude of density fluctuations in terms of using a reference scale in megaparsecs. Okay, and as I am,
Thank you, Ariel.
as I am the last speaker officially, I think it is my duty to thank the organizers. So Rogerio, Miguel, Cora, and Nelson, thank you very much for organizing this. And yeah, so I won't take more time, but thank you in the name of all the speakers for taking the time and organizing this great.
Thank you. It's not over yet. So
yeah.
Before the no, sorry. Now we go to the posters. So the poster presenters should just introduce themselves. So the first one is Beatriz Tucci. Beatriz?
You are mute, Beatriz. We cannot hear you. You are unmuted in Zoom, but muted somehow. No. You can do like sign language, but I cannot hear you.
Is it, Beatriz, is it okay if we move to the next one and then come back to you? Yeah, we cannot hear you. So let's go to the next and then back to you, okay? So next one is Maria Valentin Garcia Alvaredo. So Maria, is Maria here?
Do you hear me now?
Yes.
Yes.
So go ahead, Beatriz.
So should I introduce myself or can I give a wrap up of my poster?
Just say a few words about your poster, yes.
Words, okay. So I'm Beatriz Tucci. I'm obtaining my bachelor here at the University of São Paulo. And soon I'll be doing my master's at Perimeter. I just found out that. And I talk in my poster about some works that I developed with Antônio Monteiro Dorta and Raul Abramo. And I focused on spin bias, which is a particular case of secondary halo bias. That is the dependence of dark matter halo bias on secondary properties at fixed halo mass. And a case of very famous of secondary halo bias is assembly bias, which relates to the halo assembly history. But in my poster, I focused on spin bias, and I talked about two papers, one where we show the physical origins of low mass spin bias, that is the spin bias for low mass halos, and also another one where we use the Kinect-Sunayev-Zeldovich effect to probe spin bias in observations, where we used illustrative. That's it.
Thank you, Beatriz. Thank you. So I don't see Maria, so let's go to Tony Bonner.
Yeah. Hi, everybody. So do you hear me? Yeah.
We cannot hear you very well.
Oh, okay. Is that better now?
We can hear, we can understand, I guess.
Okay. Sorry for that. Yeah, I'm Tony Bonner, a third-year PhD student working at the Institut d'Astrophysique Spatiale in Orsay in France. And in my short talk, I was introducing a method to extract the filamentite pattern of the cosmic web as a graph passing in the middle of the galaxy distribution, and with some interesting features such as the unsupervised classification of galaxies as belonging to one of the individual filaments, but also the estimate of the local size of the filaments that are extracted. So thank you for letting me presenting that.
Thank you, Tony. Okay, so before going to the questions, we're going to take a picture, but you can already raise your hand in Zoom, okay? But let's take the picture. So open up the cameras, and Tiago is going to take the pictures. Miguel was quick.
Not really. I waited until the yes speaker, patiently. Maybe I can put a supernova in my background to help the flash.
You're done, Tiago? Okay, thank you very much. So now for the questions, as usual, it's one question per hand. So if you have two questions, you just have to raise your hand twice and go and over again. And if you're a co-host, you probably notice you cannot raise your hand. So if you're a co-host and want to ask a question, just write in the chat. So Miguel, go ahead.
Right. So I think I have a question. My first question for Ben. So when you're talking about your generalized Koch-Paczynski tests, and in general in your talk, you're talking about you're using things in configuration space, right? Did the real space, redshift space. But in cosmology, it's often very useful to go to Fourier space. So can you do something analogous to what you discussed in Fourier space? Would be advantage? Would there be advantage to doing that, or you don't think so? Can you discuss a bit about that?
I mean, this particular test is driven by, It's an interesting question. I haven't really thought about it in terms of a Fourier space test because the intuition is so simple and there's not really a particular reason for going to Fourier space, but I'm convinced you could do the same thing in Fourier space. Really, the point is just that if you measure a bunch of supernovae or other distance tracers, like say dark sirens, for example, for this, I'm not talking about the multi-probe version of this test. And if you measure a bunch of galaxies in redshift space, we know that they trace the same underlying distribution. And all you want is just that they are as highly correlated as possible, and you want them to have as much fluctuations as possible so that you can, for example, bias helps you, just, doesn't hurt you in this case. It's the more bias, the better. And so then when you have your supernovae and your galaxies, for example, you then just distort the coordinate frames because one is measured in distance and the other one is measured in redshift. So as a function of cosmological parameters, let's say you map both of them into co-moving, you just adjust the cosmological parameters until they line up. And that's really the intuition behind this test. And it's very similar to the Alcock-Pyczynski test, where that's an autocorrelation test, and there you enforce the thing that makes it work is that the local structure is that the structure is isotropic. Here in this cross-correlation test, in fact, there's a whole bunch of terms that drop out and becomes eventually you actually cancel cosmic variance because you have two different probes.
I think,
and then there's another Alcock. Yeah.
No, I think the reason.
Right. So
okay, go on, Ben.
No, I'm just to finish. It's just a pretty general way of measuring the expansion geometry, and so I showed a few examples for how to use it, but there are many more actually that one can think of.
I understand. I read your paper, but I was asking because we have similar ideas using supernovae, beyond just the standard candle, using peculiar velocities and using, lattice traces of matter. And some other people as well publish recent ideas. And usually what people do is analyze this in Fourier space. And I have some experience analyzing both in configuration space and Fourier space. And sometimes nonlinearities kick in differently, right? So it's a technical thing maybe, but if you're doing things in Fourier space, maybe it's easier to understand where you can trust your linear theory if you need that. Maybe you don't think you need that at all, but
actually, in some of these cases, nonlinearities are your friend, right? Actually, you just want there to be as much perturbation as possible. So if the nonlinearities amplify it, that's you want that to happen. And the projections I show there, which look might at first glance look very optimistic, I think are actually very conservative because, for example, for the supernova galaxy cross-correlation AP test, why cut? Actually, we cut it off in this sort of pseudo-perturbative scales, k of a half, or we have a case of k of 1, but we don't actually care about it being perturbative. Supernovas go off in galaxies, so really the scale that's relevant is galaxy size scale. So you should really be able to go down to all the way down there.
I think I agree on your cross terms. I'm not so sure on the diagonal terms, but yeah, okay, we can discuss this later.
Thank you.
Sorry, I guess you said Cora, but the microphone cracked.
I said Cora. Sorry
okay.
about the.
So the question is for Ben. Hi, Ben. Nice to see you. So I really enjoyed your talk, and I also find your work with Delphi very interesting. And I was wondering, in your application to weak lensing data, actually, this is not something that you mentioned particularly in the talk, but I was wondering from your paper, you test the Gaussianity of the likelihood, but you do, in your paper, you do a few things that Gaussianize the data. And you talk about some of these things. And I was wondering whether you think these things actually may have a huge effect or not in your main conclusions. For example, you combine beams and this Gaussianizes the data. That's one of the things.
I mean, the main point of that paper was to test whether one can use the, whether non-Gaussianities in the field, in the lensing field, have a big impact on the likelihoods. And the way we summarize that is in terms of the two-point correlation functions, which we then use to do these forward simulations. So the choice of the number of bins is not designed to Gaussianize the likelihoods or to Gaussianize the statistics of the forward model. It's simply based on technical considerations in terms of how many bins you want to keep. So Gaussianizing those summaries is not a necessity for applying these techniques. So that was not a goal in the simulation.
No, I agree that it's
not
not a necessity. I was wondering if that could change your final conclusion. At what level do you think that would change it?
I mean, in principle, keeping more bins is always better, but then information per bin goes down. And I don't recall exactly what the considerations were that led to that particular choice of binning of the power spectrum. But maybe we can talk about that offline.
Yeah, sure.
Okay, I have Maddie, and then I raise my hand on the chat, then Bruno, and then Mark. So Maddie, please go ahead.
Thank you. This is Matty, and yeah, my question is for Ben, and the talk was really interesting. So indeed, I have two questions. So the first one is, in one of your slides, you mentioned the capability of using deep learning for super resolution, essentially taking low resolution images and making high resolution images. So I was wondering how one could explain the increase in entropy or increase in information, because we can decrease resolution by losing information, but how can we increase resolution by, like, in other words, where does this information come from? And the second question,
sure.
And the second question is, most of these deep learning methods are applied on simulated data, which, there is a gap between simulations and real observations. For instance, in real data, we could have like a sky background or like contaminations, like seeing, and so forth. So what's your opinion about the applicability of these methods on real data? Thank you.
Okay, yeah, those are really great questions. So on the first point, there's no mystery. It's not generating information. What we're actually doing is we're training on a single pair of low resolution and a corresponding higher resolution simulation. And we're training the network to predict the high resolution simulation from the low resolution simulation and the initial conditions for the high resolution simulation. So the network doesn't invent additional information. The initial condition already specifies everything. So we give it high resolution initial conditions and the low resolution forward simulation. And it then maps that together into the high resolution forward simulation. If you're asking about where does that information comes from, it comes from the initial conditions that we specify. So that was the point. That was the first point. Yes, I agree. When you have forward models, this could be a talk all by itself, so I have to be careful not to go on for too long. But one way to go about this is to say, well, we're testing a particular model, and the model, if you specify the model in terms of in terms of your simulations, the simulations incorporate your physical model and they embody the physical model. And you can say that's the model we're testing, and maybe that fails, but at least it's a well-defined thing. You're putting the physics into your simulations, and that's your forward model, and you're testing that. And maybe that's not good enough, and that just means that's what science is, and you have to work harder and then improve your forward model. But the opposite side of it is that one of the strengths of this simulation-based inference is where you don't have to write down an explicit version of the likelihood. is that you can cut the data in very flexible ways too, because typically when you introduce nonlinear cuts in the data, for example, it changes the likelihoods, and it's very unclear whether Gaussian likelihoods are still okay to use, for, which is an approximation that most people use. But with these likelihood-free approaches, it gives you freedom to cut. So it's both the freedom to specify your forward model in a complicated, in a complex way, very rich way, and it's the freedom to apply designer cuts to your data, which can mess with your likelihood, but you don't care because you don't have to write down a particular form for the likelihood, or you use a very general form for likelihoods in these neural density estimators, for example.
Thank you.
That's one way of answering the question. The other way of answering the question is, well, it turns out you can also use machine learning techniques, and I mentioned these neurophysical engines as layers that map what you know you can model into the observations, and that just add degrees of freedom while respecting certain properties of the physics involved, so respecting local isotropy, locality. And so if you look at these neurophysical, that idea that so you go and model everything as much as you can, then you add in like a generalized bias layer, which is just a generalized function that maps what you can model into the observations. And then you learn the parameters of that from the data themselves. So you're then not relying on having a perfect forward model, but you're actually training the machine on the data that you're analyzing, and you can marginalize over that. That's another approach.
Thank you, Benjamin. So I register myself for a question. So my question is for Chris. I have a very naive question, Chris. So you have all these careful ways of calibrating, measuring all the correlation among the different pixels, and do all the statistical analysis. But my question is, do you have this instrument with, say, high acceleration? Because this is going to space. So I was wondering if this acceleration, when it goes out of the atmosphere, can affect the calibration, and how do you check for that?
Sure. So the answer is yes, it can, and so all of these all of these components that we use have to go through vibration testing and so on. For the slightly longer answer is a lot of the calibrations that I've mentioned, where we use flat field sources, we will have a flat field source that actually flies on the spacecraft. So there is a set of LEDs that we will be able to turn on and repeat these measurements once we are in space. So vibrations and accelerations are part of that picture. The other one, which maybe is more, maybe even more concerning from a calibration point of view, is the radiation environment in space, and the possibility that radiation will create additional defects in the semiconductors. And that could change some of the properties. So we definitely want to make sure that all of these tests are things that we repeat regularly throughout the mission to track any possible degradation.
Thank you, Chris. So next is Bruno.
Hi, thank you everyone for nice talks. My question is also for Benjamin. So when I was watching David's talk at the beginning of the week, the first thing, one of the things popped into my mind was like, oh, okay, he's taking the Borg idea and then taking the 2LPT out of it and then plugging like deep learning with some very complex learning from hydrodynamic simulations, and that's what he means to like rebuild initial conditions. That's how my brain tried to interpret. I'm not sure it was that accurate. But then I started a talk last night, and not only, well, you start with Borg, but then not only you talk about one of the applications we talk about is using learning with sims for the evolution. And well, you were also in Flatiron and stuff. So I guess my question is, do you see, I wanted to clarify in my mind what is the relationship between all these different sub-areas. And I guess the way I managed to put in one question is, do you see those deep learning methods used on very complex hydro sims for the evolution, for simulating the evolution of the universe, as supplanting Borg as some like new, more modern iteration of this original idea? Or do you see the original idea using 2LPT and more analytical predictions as still complementary in a certain way? And if so, in which way would you see this complementarity and how one could help the other in the future? I guess that's the question. Thanks.
Yeah, that's okay. There's another talk I could, I could give. How do I say that succinctly? I see the goal of, for example, this likelihood-based approach in Borg has the same goal as essentially this separate line that David mentioned, where we're using machine learning techniques to model forward, including hydro effects. They have advantages and disadvantages. I would probably consider this the Borg approach as in some ways a base case that where inserting a lot of additional physics is more complicated, because at least we're using ab initio physical models for various technical reasons, more complicated than in the other case. But on the other hand, you have a lot of control over, you don't have, I mean, the thing that there's always one little worry when you use these deep learning methods, that you're using some universal function approximator, and that you trust that the function you want to approximate is in the span of that of these function approximators, neural networks typically. And so there's that. I mean, they're very rich function approximators, so probably yes. If you train them well and you're careful and so forth, then then it probably works. But you may always have this some level of discomfort maybe with having these machines in there. That on the other hand, at some point, when there's so much evidence that it works so well in many different situations, at some point it becomes a bit conspiracy theorist style to not want to use them, just because maybe maybe you might run into a problem based on having used a neural model underneath. So anyway, there's a lot more to be said about the relationship between them. In one case, for example, we're using these samplers, and we use this that's quite heavy, but then you get these samples out, and you can then choose how to summarize these samples in terms of the initial conditions. On the other case, when you're using neural models, sometimes where you can choose what it is that you want to estimate, and that sets how you train the network, and what, for example, what loss you choose, or what architecture you choose for the network. Then once you've chosen that and you solve the optimization problem, then you have a very fast machine, but it does that one thing that you trained it to do. And then if you want to do something else, you have to go back and retrain it. So those are, but they really fit into the same overall, statistically, I think they fit into the same goal, where you're trying to find posterior approximations within the Bayesian. I think about this in a Bayesian context, all of this. And you're trying to find posterior approximations for the things that you want to learn from the data. And they're just different ways, essentially, of going about evaluating those, and different ways of using physical models, or adding degrees of freedom if your physical models aren't complete.
Okay, thanks.
Thanks,
Thanks a lot.
So I have 3 questions, and given the time, I think we're finishing with these 3 questions. So there's Mark, Claudia, and Miguel. So Mark.
Hello, hi, thanks to everyone again. My question is for Tony about the filament characterizing algorithm. So could you say something about how you regularize the filaments that you identify? A couple of sub-questions which you don't have to answer. I wonder if it might help to include walls in the description and is in addition to the filaments, and also if you have some theoretical reason to think that the minimum spanning tree that you use is should be accurate for the cosmic web. We actually found that comparing to some neuron geometries. This is, sorry for the aside, but this is not much longer. That a minimum spanning tree assumption that they use in neuroscience applies pretty well to cosmology. So anyway, I'll let you answer the question.
Yeah, thank you for the question. I hope you can hear me better now. Yeah, for the first part, for the regularization parameters, this is a very active problem in applied mathematics, and there are no prescription to find them easily and quickly. It is mainly for using training, for instance, and tests. But we have been showing that in the paper that the method is quite robust over a quite wide range of these parameters. So this is something nice. And for the minimum spanning tree topology, this is indeed something that is not completely fixed in the method, because all we need to run the algorithm is just a graph prior, and we chose it to be the minimum spanning tree indeed, because it has a long history in cosmology, and it is something that can be very easily computed using the Kruskal algorithm. But you can also input any kind of prescription, graph prescription in the prior, and just find the regularized and the smooth version of that topology. So there were another point that you mentioned that I forgot maybe.
Just if it might help to include walls.
Yeah, walls. Yeah, indeed. So in the model right now, we are just using spherically Gaussian to pave the galaxy distribution and completely omitting the wall part. It is embedded in the uniform background component, but we could think about how to describe them to take them into account. And this is actually something that I'm thinking of right now. Yeah.
Thank you, Tony. So Claudia.
So can you hear me? Can you hear me well? Yes. So this question is for Ariel. I'm wondering, in this framework that you are proposing now, if the parameters, the constraints on the parameters change.
Yes.
Hello?
Yeah, can you hear me? Yeah.
Yes, yeah.
Yes, let me, yes, so there are two basic ways in which clustering data has been used, or 2-point measurements in particular have been used to constrain cosmological parameters. One is that you do like what I call in the talk this direct approach, where you compute model predictions for your observables and you compare that for every point in the parameter space and compare that with your data and compute the likelihood. This is one approach, but a few people, including myself, have followed also within the BOSS collaboration. But the most common approach now is to first take your measurements and compress the information of the full measurements into 3 numbers, or the Sarkov-Pachinski parameters, and F sigma 8. The problem is that this F sigma 8 is measured fixing the value of H. And then this leads to problems in the results. So this is an illustration of that. These are constraints on matter and matter density and the dark energy equation of state obtained from Planck, or if you use this direct approach applied to BOSS data. And this is what happens if you do that use instead the values of F sigma 8, this compression first, and then use those values to constrain the same parameters. So you see that the results you underestimate the errors, right? This is equivalent to fixing the value of H, the analysis. So all the cosmological constraints that are derived by first compressing into F sigma 8 and Kopachinski parameters, and then looking at parameters like W, are underestimate the error mass. And there is this issue that also the results depend on the value of H that was assumed to derive these values of F sigma 8. Now the EVOS collaboration came up with a correction for this effect, for the dependency on the value of H, but this doesn't fix the fact that the errors are underestimated. So all the constraints on parameters, yes, that you derive using these values of F sigma 8 are underestimated. This also, I didn't mention this in the talk, but this is the usual approach also to compute forecasts for surveys, right? So for cosmological, when in all of these tons of papers that are written saying what is the figure of merit of the surveys, these are almost always computed in terms of first computing constraints in terms of F sigma 8, and then mapping those constraints into constraints on the dark energy equation of state parameter. As those are also affected by this issue, the figure of merit of most surveys, predictions for the figure of merit of most surveys that are derived using this compression are also wrong. This can be easily corrected by using this combination F sigma 12. Right? Of course, the best approach is always to do this direct approach, but especially for simple things like forecasts for future surveys, this is a very simple correction that would give the right figure of merit predictions for these surveys.
Okay, thank you.
Thank you, Ariel. So the last question of the workshop, Miguel.
But actually, I had a question for Matthias, but I had a quick follow-up from Ariel, because now after his answer to Claudia, I was a bit confused. So when you're talking about, the dependence on H, omega passive over H, I understand that, it can be misleading because people forget that there's a dependence on H, in many places that people neglect, right? But how much of this is fundamental, or how much of this is just people neglecting that there's an H dependence that they forgot about? Because you could still keep using megapass over H, which what people do simulations like to do, and just correct that in your analysis. Or you think, I may have missed it, is it something fundamental?
Yeah, no, so well, it's just that it is confusing, but so if you run simulations, there's no reason to use megaparsecs over H units, right? So megaparsecs over H units only make sense when you, let me share my screen, when you deal with data, right? So when you do.
But nevertheless, there's like many petabytes of simulations already megapass over H. That's a fact.
Yeah, but this is just.
So, I'm asking if there's any fundamental thing there, or can you just correct in your analysis?
No. So as I said today, so there's nothing wrong, intrinsically wrong with these units. But there are some issues with the analysis that with the comparison of constraints, observational constraints on sigma 8, and with this fact of expressing constraints on redshift space from redshift space distortions in terms of F sigma 8. So this is a plot that illustrates that. So if you want to express constraints on F sigma 8, constraints from redshift space distortions in terms of F sigma 8, you need to marginalize over H. So this is the true uncertainty. This is the orange contours here represent the results that one gets in the standard analysis where H is fixed. And the blue contours are what you get if you marginalize over H to take into account the dependency of sigma 8 on H. So if you really want to work in terms of F sigma 8, you could, but this is the error that you should quote. And the impact of H changes with redshift. So as you go to higher redshift, the constraints on H from galaxy classic measurements become worse and worse. So this error on F sigma 8 becomes increasingly larger as you go to high redshift measurements. So the errors on F sigma 8 from clustering measurements, the true error, once you account for the the dependency on age from classic measurements at high redshift would be huge, while expressed in F sigma 12, it will be just the same as what we have done. The level of accuracy that people claim we will get in F sigma 8 is actually what we will get in F sigma 12 or F times sigma measured at scale in megaparsecs. Yeah.
Okay, there's still time for my question to Matthias or Rogerio. You're the chair.
Yeah, please go ahead.
So it's a naive question to Matthias for someone who's outside this effective field theory field. So my question is, as you show in the end, as you marginalize over the bias parameters that you include to do your one loop analysis, in the end, what I see is that the information you showed in your cosmological parameters kind of saturates at K of 0.2 H inverse H over max, right? After that, you don't get much more. And the question is, even if I stop at this level, is there any extra systematics or model dependence that you are picking up from doing the one loop? So is it, I mean, can I trust this completely to be model independent result, just data? And also, what's the path to trying to get more information at higher Kmax? Is it possible, as you said, it's fundamentally related to our galaxy and formation understanding?
I was muted, sorry. Yes, in those predictions, the reason of saturation was the need to marginalize over bias parameters, nuisance parameters. I think the only way around this is to have information on these nuisance parameters from some other source. And also furthermore, to the extent that you go to higher loops in these theories, there's even more nuisance parameters. So it's more of an issue than in that plot. So if to go to higher Kmax, or even to stay at the same Kmax, but with a larger volume, which requires higher precision in the prediction, you will need to go to higher loops. There will need to be more bias parameters, and you will pay a bigger price. And so you need to get this information from somewhere else. I think you know, I don't think, on the other hand, that this is a problem of this method. Or is the fact that so regardless of how you do it with simulations or whatever you have, there will be the same number of subgrid parameters somewhere, unless you forgot to put them in, that will allow you to change these bias parameters in you know, and degrade the measurement. So this is just saying that in order to model these scales, you really need a lot of control on the subgrid model. If you're trying, so I think perhaps the way forward is some combination of some more physical models of the small scales compared with other observations of small scales, so that you can calibrate those models with observations. But I don't think it's realistic to expect there to be a less number of parameters if you do it some other way. And B, that this can be really predicted from first principles. Especially, yes, for the most part, it will have to be some combination of modeling and more other different types of measurements on small scales. So I'm not sure.
But again, just trying to understand, but so where did the priors for these parameters come from? That's what I was asking, the way when you're saying there's could be some systematic, some model dependence there. Where do you get the priors for them?
Yeah, so so that's a very good question. So the priors for those parameters. So okay, let me say two things. Those parameters come at the end two groups. Some of them, the data constrains them sufficiently well that the priors don't really matter so much. Where do we get the priors from? Mostly from some vague understanding of some halo model or halo occupation distribution, and getting some guess of how this, if it were just halos, what would these parameters be? And then making the range significantly bigger than that just to be safe. But for the most part, or for a certain group of these parameters, the prior doesn't matter, because you know these parameters then end up being measured from the data at the 10% level or so on, and there's no prior that you would be able to have anywhere that would get you to predict them some the second order bias or so on to better than 10% or so. So once the measurements already tell you what they are to 10%, the bias doesn't matter. Then the very higher order ones, yeah, we usually what happens is they don't affect the data too much because these are just the last 1% or something, and then the priors matter a little bit. We get them from ideas like this, and so there is just expanding what you get for halos and things like this. So there is a little bit of a dependence on that, and perhaps this is fixable by going to a little bit higher Kmax, and there's some room there to maybe gain some information from there.
Okay, thanks.
Okay, guys. So I think we came to the end of this, I hope, productive week. I want to thank all the on behalf of the organizing committee, Miguel, Cora, Nelson. I want to thank all the presenters because in an amazing form. It's very
You're cutting, Rogerio. Sorry, your voice cut completely.
Cutting.
Maybe turn off a video.
So Miguel, why don't you say goodbye then?
Well, goodbye, guys. Hopefully see you again in the next workshop in a couple of years, and send us feedback. And thank you for the discussion, productive discussions and videos, and everything will be on YouTube, I guess, soonish. So if you miss some talks and you want to catch up on the discussion, it will be available on YouTube and the link. Okay. And
thank you very much.
Maybe you can say some words too.
Thank you very much, and stay safe until the vaccine arrives.
Yeah, it'll be a long, stay safe for a long time. I don't know if Nelson wants to say a word as well. Nelson?
Thank you, everyone. This was great. I think everyone enjoyed it. I think it was a good experience, the format and everything. And just stay safe and see you hopefully in person next time.
Thanks,
Thank you very much.
Bye-bye.
Bye-bye.
Thank you.
Thank you.
Bye.
Thank you, everyone.
Thank you.
Bye.
Thank you.
Bye.
Bye.
Thank you. Bye-bye.